Hello, it's me again. My name is Bingyong Guo. I'm with the Center for Ocean Energy Research at Maynooth University, Ireland. Today I'm going to talk about the impact of nonlinear hydrodynamic modeling on geometric optimization of a spherical heaving point observer. In this talk, first, I will briefly introduce the background of geometrical optimization of wave energy converters, followed with the wave conditions, hydrodynamic modeling methods, control and performance criteria used in this study, and numerical studies will be conducted and discuss how these factors going to affect the optimization results. Conclusions will be drawn at the end. The geometrical optimization of wave energy converters is a complex problem. It should consider wave conditions, modeling methods, control strategies, optimization criteria and algorithms, and so on. According to a recent review paper by me and John, it concluded that there exists 6 major factors that affect the optimization results, including the vector concept, wave conditions, wave structure interaction modeling methods, PTO modeling methods, control strategies, and optimization criteria. 2 minor factors are model simplification and optimization algorithms. There are still 2 open questions. It's about how the nonlinear PTO and the nonlinear hydrodynamic modeling affects the optimization results. For geometric optimization, a core design benchmark is still missing. It is concluded in the review paper that vector geometric optimization should be an indispensable procedure at the initial stage of a vector project. In this study, we are going to discuss the influence of sea states, hydrodynamic modeling, control strategy, and performance criteria on the optimization results of a heaving spherical point observer. In this study, the wave climate at the Atlantic Marine Energy Test Site is used as the wave conditions. As shown in Figure A, we picked the most energetic sea state, the annual average sea state, and the most frequent sea state as the design sea states. Their spectrum is shown in Figure B. These sea states are represented by the Jones-Webb spectrum. Some of the typical time traces are shown in Figure C. In terms of hydrodynamic modeling methods, a linear model is developed first based on linear potential flow theory, given here. In this model, Fe is the excitation force, Fr is the radiation force, Fhs is the hydrostatic force, and Fpto is the control force. Similar with my previous presentation, a hybrid nonlinear modeling method is applied here to include nonlinear Fk force. Given that the geometrical optimization has a large number of iterations, this nonlinear model must be efficient in computation. So, the algebraic representation of nonlinear Fk force developed by Giuseppe and John is used here, which can consider instantaneous vetted surface. The weak drawback of this method is that it's only useful for symmetrical PAs. In this study, both reactive control and passive control will be used to discuss its impact on geometrical optimization results. In terms of performance criteria, the most ideal criterion is the economic one, the levelized cost of energy. However, there are only limited experience of real sea operation, thus such a model has a huge uncertainty. Technical criteria are generally used for evaluating wake performance and also for geometric optimization, including the average power and capture with leisure. There are some things between the economic criteria and the technical criteria by assuming the cost is proportional to some characteristic of the device, such as wetted area or displaced volume. Here gives some techno-economic criteria, for example, the power per sphere and the power per volume. Parametric study of radials in a wide range is conducted to get an overview of performance criteria. The influence of sea states modeling methods are given here. In Figure A, passive control is used. In Figure B, reactive control is used. The solid curve represents the results of nonlinear models, while the dashed curve represents the linear ones. The green curve represents the results of most frequent sea state, while the black curve represents the results of annual average sea state, and the red color represents the results of most energetic sea states. From these figures, we can see, regardless of all other factors, more energetic sea states are going to give a larger optimized radius. Regardless of the other factors, nonlinear FK modeling methods are going to give a larger optimized radius as well. Compare Figure A with Figure B, we can see passive control is going to give a large optimized radius. However, reactive control is more robust to sea states. The influence of modeling method and control strategies is shown here. In Figure A, the average power is used as the performance criterion, while in Figure B, capture with leisure is used. The blue curves represent the results by passive control, while the red curve represents the results by reactive control. In Figure A, the linear modeling method with reactive control may mislead the design as the heave motion exceeds the physical constraint. In Figure B, the linear and the nonlinear modeling method with passive control have global optimum and local optimum. If the parametric range is limited, the results may converge to local optimum rather than the global one. It is interesting that with reactive control, the capture with leisure in Figure B, no matter bilinear or nonlinear model, monotonically decreases as the radius increases. For the performance criterion of average power per wetted surface and the average power per displaced volume, these two techno-economic criterion monotonically decreases as the radius increases. So there's no need for us to conduct optimization for these two criterions because the lower bound of the parameter is always the optimum value. Thus, we can see that these techno-economic criteria overweight the other factors, such as the modeling methods and the control. Based on the discussions, we can see that the geometrical optimization of wave energy converters is sensitive to C-states, modeling method and control strategies, and the performance criterion. In general, a more energetic C-state is going to give a larger optimizer radius. Compared to linear method, nonlinear modeling method considering nonlinear FK force tends to give a larger optimizer radius. Compared to passive control, reactive control tends to give a smaller optimizer radius, and it is more robust to C-state valuation. The VEC geometrical optimization results is critically sensitive to performance criteria. Some of them even have multiple optimum points. The bad news is that these factors are inherently coupled, which asks for a co-design benchmark for optimization. Ongoing work focuses on CFD simulation in OpenFlow to validate the results given in this paper. Special thanks are given to the Europe Commission as this project is funded by the Marie Curie actions. Many thanks for your attention. Any questions are very welcome.